in our look at the option topics so far, we've covered some of the basics of astrophysics. We're now going to go into the HL component. So D.4 and D.5 subtopics are on HL. So it's basically just sort of taking what we've covered so far into a bit more detail. And the first thing that we're going to look at is Jeans' criterion for star formation. And this is basically sort of taking a bit of a more in-depth look at something that we covered in subtopic D.2, where we talked about the fact that stars form in a nebula or a gas cloud. So just taking that particular scenario a bit further and looking at the requirements, I guess, for a star to form. So when we look at star formation, a star forms due to gravitational attraction. So a star forms in a nebula due to gravitational attraction, and that's basically just that we've got all these gas particles that have, even though they're quite small, it's because there's no resistive forces due to air resistance or anything like that. Gravitational forces can sort of very slowly pull gas particles together, and that gravitational forces between the gas particles then starts to cause the gas to clump together, and we start to get the process of star formation. And so it's a nice easy way of stating it, but it's not just a matter of any gas cloud will collapse. So it requires a certain amount of mass when we consider a given volume. So for a given volume, there is a critical mass, and that mass is known as the Jeans mass, and that has a symbol of Jeans mass. The symbol that we use there is M with a subscript J, and the reason why we need that mass is so that there's enough gravitational force that can actually pull the clumps of gas together. So basically, the mass of the gas cloud itself has to be greater than the Jeans mass. And so if we use capital M to represent the mass of the gas cloud in that given volume, then we'd say that if M is greater than the Jeans mass, a star will form. If M is less than the Jeans mass, then the star won't form. So it's one way that we can consider that particular scenario. So if we look at what the properties of a gas cloud are that will allow a star to form, there's three things in particular that we need to be aware of. So a star is more likely to form given certain properties of the gas cloud, or if the nebula, and again considering there's a few different quantities here. The first one we're going to look at is the fact that if it has a large mass, so a large mass basically means greater gravitational attraction, and so more chance of the star forming. The second one is a small radius. Even if the mass is quite small, a small radius will allow enough gravitational force in that small volume in order for the star to form. And the last one is a low temperature. Now you might look at that and think, well, why would temperature have an effect? We're going to have a bit more of an in-depth look at this from a different perspective. So the perspective we're going to look at is from an energy perspective. So not just dealing with mass, dealing with the energy involved as well. Before we talk in too much more detail about this scenario though, I want to just very quickly refresh your memory. So the first thing to remember is that EP The one that we're interested here is gravitational potential energy. So that's due to a mass's position in a gravitational field. And in the case of a nebula, all of the gas particles would have their own small gravitational fields around them, and so they're attracting other gas particles. So each particle would have a certain amount of gravitational potential energy. Important to remember here that EP is equal to 0 at infinity. So when the particles are an infinite distance apart, then there is no potential energy. What that also means is that EP, as a result of that, is a negative value. So important idea to keep in the back of your mind. We'll come back to that in a second. The other energy form that we're interested in is kinetic energy, and that's due to the motion of the gas particles. Now, just tying back into these properties that we identified up here, what we're really saying then for a low temperature, we're saying that it has a low kinetic energy, or the gas particles have low kinetic energy. If we're talking about a small radius, that means the particles are close together, so it means that the magnitude of the gravitational potential energy is going to be quite large. The large mass really ties into both of those. Large mass can sort of cause an increase in kinetic energy, but it can also cause an increase in potential energy, so not quite as critical a factor to talk about when we're looking at the energy perspective. So those two quantities of energy, we can now sort of, instead of phrasing it in terms of mass, we can phrase Jean's criteria for star formation in the context of the energy involved. So Jean's criterion for star formation basically relates to how much of each of those two forms of energy are present in the gas cloud. And the way that we would state it, there's two ways that we can consider this. The first way is basically just that a star will form when the sum of those two potential energies is less than 0. So the sum of the, more specifically here, when the sum of the potential, so gravitational potential, and kinetic energies of all of the gas particles, kinetic, so we're not just talking about one or two, we're talking about all gas particles is less than 0. And we can express that in an equation, and basically we're just sort of looking at the fact that EP plus EK has to be less than 0. So that's the criterion just stated in words. Another way to think of it that's probably a little bit more understandable, and seems to be the way that past exam questions have been answered, or the marking scheme has been phrased. If we consider that, we know that EP is going to be less than 0, so it's a negative value. EK is going to be a positive value. So basically we're saying that for the sum of these two to be less than 0, the magnitude of EP has to be greater than the magnitude of the kinetic energy. So that's the alternative way to consider it. What that means is that there's more potential energy than there is kinetic energy. And notice here we're talking specifically about the magnitude, so we're not worrying now about the fact that potential energy has a negative value. We're just saying that the quantity of potential energy is greater than the magnitude of the kinetic energy. So the way that we can write this now in equation form, slightly different, but basically the same idea, is that we're saying that the potential energy is greater than the magnitude of the kinetic energy. Note that I'm not highlighting those; they're not actually in the data booklet. It's more just a concept to understand. So one other way to interpret this, then, so both of these, the way that we've expressed both of these, you can consider it to basically mean that the particles themselves have to be moving slow enough so the kinetic energy is small enough, and we know that kinetic energy relates directly to speed. So particles must be moving slow enough, and another way to interpret that is that the gas cloud is cold enough that gravity has enough pull or enough influence to cause the gas particles to fall in together, collapse together. So if the kinetic energy is too great, it means that the gas particles will keep sort of flying past each other, and they won't actually start to collapse inwards because they're moving too quickly. So that's Jean's criteria for star formation. What we'll look at in the next video is what happens after the star forms, so looking at the nuclear fusion that then begins to occur in the core of the star, and we'll have a look at some of the processes that are occurring in that sort of situation.